Hello, everyone. My name is Giseli Lopez, and I'm going to be talking about magnitude data of Soviet underground nuclear explosions and how it may help us in investigating the MBMS discriminant. So the former Soviet Union set off 496 underground nuclear tests and 122 peaceful nuclear explosions between 1949 and 1990. Sourcing data from various publications, we have found varying degrees of information for at least 437 underground nuclear explosions. As an example, the map on the left shows 296 UNEs for which location data is available. Two test sites are represented by this data set, Novaya Zemlya and the Semipalatinsk test site. The peaceful nuclear explosions, by definition, are scattered outside of test sites across the former Soviet Union. This is a large data set with a long history, and it carries the advantage of being synchronous with high-quality waveform data starting in the early 1960s, courtesy of the worldwide standardized seismographic network, which we hope to exploit in future work. The Muller and Murphy model has been used for decades in the seismology field as a basis for describing explosive sources. So they interpret such a source as an isotropic pressure function acting upon a spherical surface at the elastic radius, which is the distance at which the rock surrounding a UNE begins to behave elastically. The pressure function is characterized by Muller and Murphy as a variation on the unit step function, with terms that are dependent on the peak shock pressure and the steady state pressure. So broadly speaking, the explosion energy creates two types of seismic waves: body waves, which travel through the Earth, and surface waves, which travel along the surface of the Earth. And these waves are distorted by various processes as they propagate out from the source, but ultimately they are measured as ground motion recorded by seismographs at seismic stations. So we calculate magnitude by adding a distance correction to the logarithm of the ratio of the amplitude to the period of a wave signal, which we measure from seismograms. So as an example, this diagram here is showing how we extract waves from a raw broadband signal pictured on top to calculate two of the classic magnitudes used in seismology. So the second signal shows the resulting signal after applying a low frequency filter to broadband data. The filter clearly captures the long period surface waves from which we measure MS. A high frequency filter is applied to the broadband data, renders the last signal, which shows the short period P waves from which we measure MB. And we compare these two magnitudes in the form of the MB-MS discriminant. So being two different sources, earthquakes and nuclear explosions produce distinctive waveforms and give differing MB and MS values. Compared to earthquakes, nuclear explosions produce body waves that are more energetic than surface waves, and this dissimilarity is the main foundation for the MB-MS discriminant. Several monitoring authorities use the discriminant to assess whether seismic waves come from an earthquake or an explosion. And although this method has been in use since the 1960s, it's still not fully comprehended why it works so well. And it has also been shown to fall short of expectations. For example, this figure on the left shows the proximity of some tests carried out by the Democratic People's Republic of Korea to the event screening line that was previously used by the International Data Center of the Comprehensive Test Ban Treaty Organization. So that's this black dashed line. And the ambiguity of these explosions to the old IDC screening line prompted a revision to the IDC screening line, which is plotted here in red. And it also sparked a reassessment of the MBMS discriminant. So we hope that we can use the copious amounts of Soviet UNE data available to enlighten our understanding of why MBMS did not work as expected for these North Korean explosions. A lot of the uncertainty in the discriminant comes from a lack of concrete knowledge about how UNEs generate surface waves. And recent work by us investigated Soviet UNEs to show that the scale depth of burial has a predictable effect on the generation of long period surface waves, which we believe is related to the scatter between MB and MS. So we're interested in exploring how this recently identified relationship can be used to enhance our understanding of the discriminant. A more thorough understanding of MBMS and its shortcomings is aligned with the NNSA mission of monitoring and non-proliferation. So while other source discrimination methods exist, MBMS is primarily and internationally used in the monitoring efforts prescribed by the Comprehensive Test Ban Treaty. So it's essential that we have confidence in this tool, especially when we're monitoring regions with a sparse station coverage and a lack of access to local seismic data. So for this phase of the project, the main approach was to gather existing Soviet UNE data, especially information about magnitude, depth of burial, and yield. Our preferred magnitude measurements come from the Black Nest Group of the British Atomic Weapons Establishment. They are network averaged and calculated using a maximum joint likelihood method that removes upward bias resulting from signal obscuring noise at stations. We collected two different sets of explosion yield measurement. The first set was estimated using a body wave magnitude yield relationship derived by Howe et al., specifically for UNEs at the Semipalatinsk site, with MB measurements coming from Black Nest, of course. The second set was taken from an official report by the Russian Federation. Device depth of burial information came from reports published by scientists at the Kazakhstan National Data Center, and values for scale depth of burial were calculated simply by dividing the depth of burial by the cube root of the estimated or reported yield. So once the data was collected, we investigated potential relationships between the different metrics. All in all, we found 115 UNEs that had data available for the metrics of interest. The different symbols in this scatter plot on the right shows that about half of the UNEs were tests conducted at Semipalatinsk, and they're marked by the orange circles. The other half were peaceful nuclear explosions, marked by blue X's. So we can see that the PNE subset trends towards a smaller MBMS than the Semipalatinsk tests, although there is some overlap between the two subsets of data. Additionally, the revised IDC screening line is plotted on the scatter plot in red, and events that fall above this line are considered to have a high probability of being earthquakes. We also plotted 4 North Korean explosions, um, and we can see that a few of these PNEs lie in the vicinity of the North Korean explosions. And we also note that these PNEs have the largest values for scale depth of burial in the data set. This explosion in particular has a scale depth of about 1,008 meters per cube root kiloton. And this explosion has a scale depth of 493 meters per cube root kiloton. The histogram of the data shows the distribution of the collected depth of device burial data. The tests have a distribution with a strong positive skew, whereas the PNEs are normally distributed around 1,000 meters. We have observed a weak negative linear association between scale depth and MBMS. The revised IDC screening line is plotted for reference in red. So in this figure, the so-called earthquake zone is below the IDC screening line, but we can see that these explosions, as the scale depth increases, are approaching MBMS values that are typical of earthquakes. Okay, so we observe these trends in the magnitude data, and namely that MBMS is small for overburied explosions. We believe that this finding is consistent with the asymmetric elastic source model proposed by Howe et al. 2020. The diagrams pictured on the right show how the aspect ratio of the spherical surface upon which the pressure function is acting becomes truly isotropic. So it approaches a C value of 1 as devices become overburied. And a decrease in the aspect ratio is associated with the generation of stronger surface waves. So we believe that a source model that accounts for the relationship observed here may provide a better physical understanding of the MBMS discriminant and perhaps can explain the shortcoming of the tool when it came to the North Korean explosions. So to conclude, magnitude, yield, and depth of burial data of Soviet UNEs provide controls on explosion source models, which may result in an improved comprehension of MBMS. The trends presented here seem to be consistent with the asymmetric elastic source model proposed by Howe et al. And of course, there remain other effects on magnitude that must be investigated. For example, source medium and geographical magnitude bias. And a quantitative examination of the digitized analog records of broadband seismic signals pertaining to remarkably shallow and deep UNEs builds on the observations presented here and tests the validity of our proposed asymmetric source model. Thank you.